Hello dear students. In this video, we will solve some problems from the topic Newton's second law. This is the part of applications from the Newton's law. And the exercises that we do in this session are from the textbook University Physics by Hugh D. Young. So first, let us review what Newton's second law is. So we had learned about the statement of Newton's second law. We had learned its mathematical statement as well. So Newton's second law states that when the net force acting on a body is non-zero, the body will accelerate. The sum of net forces acting on a body will result in an acceleration that is along the direction of the force that is being applied. This single equation can in fact be resolved into three separate equations, which is in the x direction, y direction, and in the z direction. For two-dimensional problems, you can write it as simply two equations, which are sum of all the x components of forces results in an acceleration along the x direction, and sum of all the y component of forces results in an acceleration along the y direction. So before we move in to solving different problems, let us see the problem solving strategy that we can adopt in order to solve Newton's second law problems. It consists of three parts. First, we need to understand about the setup of the problem. To understand this, the best way is to sketch the situation. If possible, draw the situation. Then from that, you can label all forces which results in the free body diagram. Then the next step is to consider the most suitable coordinate axis, the x and y axis, that can help you solve this problem. And from that, write equations, apply Newton's second law for different directions, for different coordinate axes, and thus form the basic setup of the problem. Now the second part includes executing the solution. In this step, you will be resolving the forces along different component directions, along different coordinate axes, and sometimes you will not be knowing about all the quantities. So you will have to sort out which quantities you know and which one are unknown variables. You may write all the necessary equations, including Newton's second law, as well as some other previous mechanic equation in order to find out these unknown variables. And then solve these equations mathematically and simplify to get the required variables. Now the third part of finding or solving Newton's second law problems involve evaluating your answer. In this part, you will have to check whether your answer has correct units, algebraic sign, and also check if whether the result make any sense. For example, this can be done using substituting certain extreme values. What happens when velocity is 0 or when the angle is 0 and so on. And in that way, you can evaluate your answer whether it is correct or not. Now, applying these methods, let us solve one problem from Newton's second law. This is example 5.8 from our reference textbook, tension in an elevator cable. Let us read the problem. An elevator and its load have a combined mass of 800 kg. The elevator is initially moving downward at 10 meter per second velocity. It slows down to a stop with constant acceleration in a distance of 25 meter. What is the tension T in the supporting cable while the elevator is being brought to rest? So the first part of the problem is setting up the problem. You have an illustration here. If the illustration is not provided, you will have to draw it and understand. You can see an elevator is falling down. It initially has an initial velocity of 10 meter per second, but it comes to a stop. That means its final velocity is 0 when it has traversed the distance of 25 meter. You are also given with this total mass of the system, which is 800 kg. And you are asked to find the tension that is felt on this cable. Now, can you draw the free body diagram of this particular case? The free body diagram can be plotted like this. So if you consider this entire elevator as a point mass, the weight of the body is acting downwards and the tension on the cable acts upwards. So the total force that is acting on the elevator is given by the tension of the cable plus the weight of the body acting downwards. This is the sum of all the y components of forces. Now what does Newton's second law say? Sum of all y components of forces that results in acceleration along the y component y direction. It also states that sum of all the x component of forces results in acceleration along x direction. But since there are no forces that is acting along the x direction, this is 0 and the body has no acceleration along the x direction. But here the net force acting along the y direction is non-zero. Therefore, it will have an acceleration along the y direction. So we can write T plus minus W, which is the sum of all the y components of forces, that is equal to m into Ay. So T plus minus mg equal to may, or rearranging the terms we get T equal to m into g plus ay. So you are asked to find T in this question, and for that you need mass, acceleration due to gravity, which are all known. Mass is given in the question itself. Acceleration due to gravity is a constant, and Ay, which is not directly given in the question. So in order to find Ay, you will have to resort to other methods. So let us bring in another equation, which is v square minus u square equal to 2as, because in the question you are given with the initial velocity, which is 10 meter per second, the final velocity is 0 meter per second, and the displacement, which is denoted as s, happens in 25 meter. But you will have to notice that this displacement happens along the downward direction. Initially from a position, it's slowing down and stopping at a more negative position along the negative y direction. So you will have to put a minus sign here. The displacement is actually minus 25 meter. Now substitute these values into this given equation number 1 and find Ay. You will see acceleration equal to v square minus u square divided by 2s, which is equal to 0 square minus 10 square divided by 2 into minus 25, which is actually minus 100 divided by minus 50, which is equal to 2 meter per second square. So this means that the body has an acceleration along the positive y direction. We know the body is decelerating along the negative y direction. It can also be understood as an positive acceleration along the opposite direction. So substitute all the values, the mass of the body, the acceleration due to gravity, and Ay. 800 kilogram multiplied by 9.8 plus 2 meter per second square, and find the answer. That much Newton will be experienced by this particle. So this is the answer worked out in your textbook. You will see that 800 multiplied by 9.8 plus 2, that results in 9440 Newton. So the key concept that we learn is that if an object suspended from a cable is accelerating vertically, the tension in the cable is not equal to the weight of the object. So usually we had learned that when a tension is acting on a cable, we usually equated it with the weight of the body acting downwards. Tension is equal and opposite to weight. But that's only the case of Newton's first law. When Newton's second law is working in the context, working in a particular scenario, we know that the body is accelerating. Then the tension will be different. So on an elevator cable which is moving up or slowing down, the tension on the cable will be different. Let us do another problem from the Newton's second law topic. This is example 5.9 from your textbook, which is apparent weight in an accelerating elevator. Let us read the question. A 50 kilogram woman stands on a bathroom scale, a weighing scale, while riding on the elevator in example 5.8. So in the previous example, within the elevator, a 50 kilogram woman is standing. While the elevator is moving downward with decreasing speed, what is the reading on the scale? So let us do this problem. First, let us draw the free body diagram. So suppose the single woman is denoted as a single point. The weight of the lady is acting downwards. Weight is given by mg. Since she has 50 kilogram, 50 multiplied by 9.8 yields 490 Newton, which is the weight of the woman. There is a normal force acting upwards. So sum of all these forces results in acceleration along the y direction. Mass multiplied by acceleration along the y direction. So in this particular case, sum of all the y components of force is equal to the normal force plus minus mg. That results in may. So you can calculate the normal force to be mg plus may. Substitute all the values here. So since this is the previous example itself, we had already found out ay to be 2 meter per second square. So substitute all the values. M here it should be the mass of the lady alone, not the mass of the full elevator. Why? Because the lady alone stands on the weighing scale. The elevator is not suspended on the weighing scale. The weighing scale only experiences the mass of the woman. So the normal force is given by 590 Newton. So this will be the weight experienced by the bathroom scale. So let us modify the problem. This is a homework problem for you. What would the woman feel if the elevator were accelerating downward so that Ay equal to minus 2 meter per second square? So in the previous example, we saw that a 490 Newton woman was weighing higher 590 Newton when the acceleration was Ay equal to 2 meter per second square. So instead of this 2, if it is a minus 2 meter per second square acceleration, what would be the weight of the woman as measured by the weighing scale? So from this exercise, you can see that weight can vary from context to context, even when the lady has the same mass. So the key concept that we learned from this problem is that when you are riding in an accelerating vehicle such as an elevator, your apparent weight is in general not equal to your actual weight. The apparent weight is measured by the weighing machine may change depending on the acceleration of your frame. Now let us do another problem from Newton's second law topic itself. This is example 5.10, acceleration down a hill. A toboggan loaded with students, total weight W, slides down a snow-covered hill that slopes at a constant angle alpha. So this is pictorially represented here. The toboggan is well waxed, so there is virtually no friction. What is its acceleration? So there is no friction between the surface and the toboggan. And students, the total weight is W. It's sliding down. The angle of inclination here is alpha. You're asked to find the acceleration of this whole system, the toboggan together with the students. So first, let us draw the free body diagram. Consider the full system of students along with the toboggan as a single point. What are the forces acting on it? We can see that their weight always act downwards and the normal force act perpendicular to the surface. So the weight of these students along with the toboggan, which is W, acts downwards, and the normal force acts perpendicular to this surface. So they are acting at different angles. So if this is alpha, using trigonometry, you can find that this angle is also alpha. So I give it as a small exercise for you. Prove that if this angle is alpha, you can see that for this triangle, this angle is alpha as well. So in this triangle, this angle is alpha. So given alpha, you can actually split W into components. So here comes an important step in solving this problem. You can choose any set of coordinate axes in any direction to solve a particular problem. But usually, the best choice will be to take the x-axis as the particular direction along which the body is moving, and y-axis as its perpendicular direction. That is, x-axis as the surface and the y-axis as its perpendicular direction. So usually weight will be the force that we will have to split into components. Other forces will usually lie along the direction of the surface or will be perpendicular to that surface. So let us split these weight into components. Why do we split weight into components? Ultimately, we need all the forces either to be in the x direction or to be in the y direction. Then only we will be able to sum them as sum fx or sum fy. So if weight is in one direction and the normal force is in another random direction, we may not be able to apply Newton's second law. So we will either have to split normal force into components or the weight into components. So here we split weight into two different components. So the weight can be split into components as its adjacent side of alpha, it will become W cos alpha, and the opposite side, that will become W sin alpha. So this is W cos alpha and this is W sin alpha. We choose this direction as our y direction and the surface direction as our x direction. So what are the forces that is acting along the y direction? It is W cos alpha and the normal force. What are the forces acting along the x direction? It is W sin alpha. So we have two separate equations. We can write sum of all the y components of forces, that is equal to W cos alpha plus the norm, that is W cos alpha, which is along the negative y direction, plus the normal force. This is the y component forces. This should sum to 0. Why? Because the toboggan is not moving up or falling down. It is remaining stable along the y direction. So we can see sum of all the y components of forces should be 0 or normal force equal to W cos alpha. Now we can see that along the x direction there is only one force. Sum of all the x components of forces results in acceleration along the x direction. Sorry, x components of forces. So we can see here only W sin alpha acts along the x direction. That results in max. Now W is mg, right? So mg sin alpha equal to max. M will cancel out and we can write the acceleration along the x direction is equal to g sin alpha. So irrespective of the mass of the toboggan and students, the body will have a constant acceleration that depends on the angle of inclination. So when you ride on Wonderla slides, irrespective of your mass, everybody will have the same acceleration given by the angle of inclination of that particular ride. So this is how your textbook executes this problem. Acceleration can be found to be g sin alpha. The key concept that we learned from this problem is that in problems with an object on an incline, it's usually best to take positive x direction for that object to be down the incline or along the surface. The force of gravity will then have both an x component and a y component. Let us do another problem related to Newton's second law. This is example 5.11, two objects with the same acceleration. Let us read the problem. You push a 1 kilogram food tray through a cafeteria line with a constant 9 Newton force. You can see it here. The tray pushes a 0.5 kilogram milk carton. So here this is the milk carton. The tray and carton slide on a horizontal surface so greasy that friction can be ignored. Find the acceleration of the tray and carton and the horizontal force that the tray exerts on the carton. So you have two parts for this question. In the first part, you have to find the acceleration of the tray and the carton and the horizontal force. In the second part, you have to find the horizontal force that the tray exerts on the carton. So let us first take the first part of this problem. In order to solve this first part, there can actually be two methods. You can either consider this tray and the carton as two separate masses and find separate equations for each of them. Or in method 2, you can consider these two as a single entity, as a composite object on which a single 9 Newton force is acting, and then solve like that. So I will be using the second method in order to solve this first part. So draw the free body diagram. On the single body, which consists of this tray together with this carton, a force is being applied along this negative x direction. The total weight of the body is acting downwards, and the normal force supported by the table is acting upwards. So since the body is stable along the y direction, we can write sum of all the y components of forces adds to 0. That means the normal force plus the weight of the body acting along the negative direction, that sums to 0. Now, sum of all the x components of forces, that results in acceleration along the x direction. So here, in 9 Newton force is applied towards the left direction. You can take it as the right direction as well. So 9 Newton force results in, you can put a minus sign here if you need, results in the total mass of the body, which is the mass of the carton plus the mass of the tray, multiplied by acceleration. So acceleration is given by minus 9 divided by the sum of the masses. So that results in 9 divided by 1 plus 0.5. 9, you can either put a negative sign, assuming that it moves towards the left. You will get minus 6 meter per second square as the answer. The minus sign indicates that you are applying force along the negative x direction and the body is moving along the negative direction. You can also take it as the positive direction and put a positive sign for both force as well as the acceleration. So we have solved the first part of the problem. The second part, you have to find the force applied by the tray on the carton. So in order to find that, you will have to identify carton and the tray as separate objects. The carton is a body that has 0.5 kilogram and it is accelerating at 6 meter per second square as obtained by the previous equation. So if a body has to have this much acceleration, what force should be acted upon it? So it is given that the force applied by the tray on carton should be equal to the mass of the body multiplied by its acceleration. Otherwise, it won't be moving at that acceleration, right? The force that the carton requires is completely provided by the tray alone. So this comes across as 3 Newton. So at this force should be applied by the tray on the carton so that the carton is moving at 6 meter per second square acceleration. So the key concept that we learned from this problem is that when two objects are touching each other, the free body diagram for each object must include the force exerted on it by the other object. In the method 2 that we did, we actually considered it as a composite object. But for the second part of the problem, you will have to see that these are separate objects, and for the carton alone, you will have to draw the free body diagram. So in that case, it is accelerating along this direction. Its mass is given. So if its weight is acting downwards, normal force is acting upwards. Since it is accelerating along the x direction, that much amount of force should be there. So that is how we do the second part of the problem. Let us do one more problem from the Newton's second law topic. This is example 5.12, two objects with the same magnitude of acceleration. Figure shows an air track glider with mass m1 moving on a level frictionless air track in the physics lab. The glider is connected to a lab weight with a mass m2 by a light, flexible, non-stretching string that passes over a stationary frictionless pulley. Find the acceleration of each object and the tension in the string. First, let us draw the free body diagrams. We have two separate objects here. One is the glider and the another one is this lab weight. So we have to draw two free body diagrams. For the glider, its weight is acting downwards and the normal force is acting upwards, which balances out each other along the y direction. Along the x direction, the tension on the rope pulls it towards the right direction and hence it is accelerating along the positive x direction. And for the lab weight, its weight is acting downwards. If m2 is its mass, m2g is its weight, and the tension on the rope acts upwards. The imbalance in these forces results in an acceleration along the y direction for the lab weight. So these are the free body diagrams. Let us now write the Newton's equations for both these bodies. For the glider, along the x direction, we saw that only the tension acts, and therefore we can write sum of all the x components of forces equal to m1 into acceleration along the x direction. Now along the y direction, two forces were acting, the normal force and the weight. They balances out each other and it is 0. It is not accelerating along the y direction. The lab weight, which is held vertically, there are two forces acting on it, which is the tension force that is acting upwards plus the weight of the body that is acting downwards, and that results in an acceleration along the downward direction. So I put m2 into minus a, because the body is moving down and there will be an acceleration along the negative y direction. So this equation can be rewritten as minus t, or t equal to m2g minus m2a. So we have one equation m1ax that is equal to t, and the second equation t equal to m2g minus m2a. So equating these two, I get m1ax, which is also equal to m1a. Both are accelerating with the same acceleration. m1a equal to m2 into g minus a, or m2g, sorry, you will have to find the acceleration, so do not take it as common. m2g minus m2a, take it to the other side and take acceleration as common. A into m1 plus m2 equal to m2g, or acceleration can be found to be m2 divided by m1 plus m2 into g. So depending on the ratio of the masses of m1 and m2, the total system will be accelerating. And substituting to find the tension on the string, you will have to substitute it back into the equation t equal to m1a. We found acceleration now. Therefore, tension on the string can be found to be m1 m2 divided by m1 plus m2 into g. The key concept that we learned from this problem is that if two objects are connected by a string under tension, both objects have the same magnitude of acceleration but may accelerate in different directions. The lab weight was accelerating along the downward direction and the glider was accelerating along the plus x direction. Choose the positive x direction for each object to be in the direction of its acceleration. But in this problem we solved by choosing the downward direction is the y direction itself. You can choose coordinate system according to the best choice that will enable you to solve the problem. I hope these problems were clear for you. Thank you for listening.